In this video, we shall see the operational amplifiers. The introduction to operational amplifiers. This is the symbol of an operational amplifier. So it has got two input, V in 1 and V in 2, and there is a single output, V out. So output expression is given by A0 times the difference of V in 1 minus V in 2. So A0 is the open loop gain of this operational amplifier. So V out, the output voltage, is given by the gain times the difference of the input voltage, that is V in 1 minus V in 2. The other representation of the op-amp symbol can be by this symbol. So now here the difference between this and this is, there is a VCC and VAE supply voltages are mentioned. This is how the model of that op-amp looks like. Now this is V in 1, this is V in 2, and this is the voltage gain parameter, that is A0 times V in 1 minus V in 2. So this is the output voltage source whose amplitude is given by A0 times V in 1 minus V in 2. Now we should see the working of operational amplifier. So we shall consider the first circuit where the input voltage is given to V in 1 and V in 2 is grounded. So we know that the output expression is given by V0 multiplied by V in minus of V in 2. As V in 2 is 0, so the output voltage is given by A0 times V in. Corresponding to this output expression, so we are writing the transfer characteristics of this operational amplifier, which has got a straight line with a slope of A0. Now similarly, in the second circuit, here V in 1 is made 0 and V in 2 is given with the input voltage. Now corresponding to this expression, the output expression, which is given by A0 into V in 1 minus V in 2. So we got the expression as V out is equal to minus A0 times V in 2. So here also there is a straight line with a slope of minus A0. We shall see another application of an amplifier. Now we can see the output voltage is fed back to the input voltage V in 2. So V in 1 is V in. So this is the output expression what we have. So V out is nothing but A0 times V in 1 minus V in 2. So V in 1, which is the voltage at the non-inverting terminal, is actually the V in. But V in 2, the voltage at the inverting terminal, that is minus, is equal to V out. So substituting that V in 1 as V in and V in 2 as V out. So we get the expression for V0 by V in. That is, the gain of this amplifier is given by A0 divided by 1 plus A0. So this is, suppose if A0 is very large, so then 1 plus A0 is almost equal to A0. So we get this gain of this amplifier with this feedback as almost equal to 1. So that's why this is the name of unity gain amplifier. So this is also called as voltage follower. So this is what is the fundamentals of op-amp. So we know that V in 1 minus V in 2 into A0 is V out. So from that expression we can write V in 1 minus V0 is nothing but V out by A0. If A0 is infinity, we can write V in 1 is equal to V in 2. So this is under ideal condition. So let us consider a non-inverting amplifier. So this is a circuit diagram of a non-inverting amplifier. The input is applied to this non-inverting terminal. The output, at the output we are having two resistors R1 and R2. So from this junction, the inverting input is applied as V in 2. So we should see this is the fundamental expression of the output voltage, which is nothing but A0 times V in 1 minus V in 2. Since we are assuming A0 to be infinity, so V in 1 is equal to, of course now this is, as we can see now, so V in 1, which is at this point, is actually the input voltage V in. So let us see what is V in 2. The voltage at V in 2 is nothing but V out multiplied by R2 divided by R1 plus R2. This is due to the potential divider action. V in 2 is given by R2 by R1 plus R2. We also know that from this expression, so V in 1 minus V in 2 is nothing but V naught by A naught. So from which we can write V in 1 is equal to V in 2 if A naught is equal to infinity. So since this V in 1 is equal to V in, so we know that V in 1 is equal to V in 2. So from which we can write, okay, V in 1 is nothing but V in 2 is nothing but this expression which is being rewritten here. So using this expression we can get the gain of this non-inverting amplifier as V0 by Vin is equal to 1 plus A1 by A2, where A1 is the feedback resistor connected between the input and the output, and R2 is a resistor connected between the inverting terminal and the ground. So this way we can obtain the gain of non-inverting amplifier under the condition A0 as infinity. So let us consider the same non-inverting amplifier. So let us try to see this is the same non-inverting amplifier. So this is a case. So we have the output expression given by Vout is equal to V0 into V in 1 minus V in 2. So this V in 1 is equal to V in. The voltage at this point is equal to V in. Okay, V in 2 is nothing but R2 divided by R1 plus R2 into V out. Now since we know that from this expression V in 1 minus V in 2 is nothing but A0 by V out by A naught, and so let us this is the expression, this is the circuit diagram, and this is V in 1 minus V in 2 is nothing but V out by A naught. So upon rewriting this expression we can get the final expression V out by V in as equal to 1 plus R1 by R2 into 1 minus 1 plus R1 by R2 into 1 over A naught. So this term, the second term of this equation, which is nothing but 1 plus R1 by R2 into 1 over A naught, is nothing but the gain error term, which is deciding what is the gain of the amplifier. Let us consider the inverting amplifier. This is like a diagram of the inverting amplifier using op-amp. So R1, R2 are the resistors which are used to R1 is the resistor connected between the input, output and the inverting terminal. R2 is the resistor connected from inverting terminal to the input voltage. Now let us assume that this is the equivalent circuit by writing the current expression as the current flowing through that is V in by R2. That is here the voltage is 0. By virtual ground the voltage here is 0. So we will have the expression for the current that is flowing through this as V in by R2. So this is the fundamental expression what we have for the inverting amplifier. So V out is given by A0 times V in 1 minus V in 2. So we also know that the expression for V in 1 minus V in 2 can be written as V out by A0. Suppose if A0 is equal to infinity, we will write V in 1 is equal to V in 2. And here we know that V in 1, the voltage at the non-inverting terminal, which is usually named as V in 1, is equal to 0 because it is grounded. So what is the current that is flowing, because this is ground, so the voltage at this point is also 0. So we can actually find the expression for the output voltage to input voltage by equating the currents that is flowing in this arm. So now you can see the current that is flowing from through R1 is nothing but 0 minus V out by R1. That's what is here. And the current that is flowing through R2 is nothing but V in minus 0 by R2, which is given by this expression. Equating those two currents that is flowing through R1 and the R2, so we get the expression of minus V out by R1 is equal to V in by R2. So from which we can get the gain expression for this inverting amplifier as minus R1 by R2. So let us consider a case where V out is the open loop gain of the amplifier is not infinity. So previously we got the expression for V out by V in as minus R1 by R2, which was under the case where A0 is infinity. if A0 is not infinity, so this is the voltage at this point. Let us consider it as Vx here. This is 0, this is Vx. So we know that since this is Vx, the current that is flowing here is Vin minus Vx by R2. The current that is flowing through R1 is given by Vx minus Vout by R1. That's what is here. So equating those two currents, and we also know that the output expression Vout is given by V0 into V in 1 minus V in 2. So since V in 1 is 0, V in 2 is Vx, so we get output expression as minus A0 into Vx. So substituting all these, we get the expression for V out by V in as given by over here. So it can be again rewritten, and it can be written in the simplified form as V out by V in is given by minus R1 by R2 into 1 minus 1 over A0 1 plus R1 by R2. So this is under the case where this particular term, that is 1 over A0 into 1 plus R1 by R2, should be far less than 1. If that is the case, then we end up with the final gain expression as minus R1 by R2 into 1 minus 1 over A0 into 1 plus R1 by R2. Let us see other applications of the operational amplifier. So let us consider a network where we have Z1 as an impedance connected between the output and the inverting terminal. Z2 is connecting input and the inverting terminal. So we know that V in 1, so that is the voltage at the inverting terminal is 0. We can write V0 by, and the voltage at since this is 0, if you are assuming A0 to be infinity, the same voltage appears over here. So we can obtain the expression for V0 by Vin as minus Z1 by Z2. So this is, it was exactly equal to minus R1 by R2 in case of inverting amplifier. So let us consider this. So instead of Z1, Z2, what we have here, so in place of Z1, let us have a capacitor. In place of Z2, we have a resistor in this integrator circuit. So now this is replaced by C1, now this is R1. So in place of Z1 we have the capacitor, in place of resistor Z2 we have a resistor R1. So we can write the expression for the current that is flowing here. The current that is flowing is Vn minus 0 by R1. The current that is flowing here is minus C1 integral of, derivative of the output voltage, because we know that current through a capacitor is nothing but C into dV by dt. So here the voltage is V out, the differential voltage will be dV out by dt. So finally the output expression can be written as minus 1 over R1 C1 integral of Vn into dt. So this shows that the output voltage is the integral part, integration of the input voltage. So that's why the name integrator. So it can also be written in the Laplace form. So because the impedance of capacitor in Laplace transform is 1 over C1s. So this is the Laplace of resistor R1. So we get the gain as minus 1 over R1 C1 into S. So this is the Laplace transform of the gain of your integrator circuit. Similarly, we can obtain a differentiator output where we can see the again on the same lines. In place of Z1 we have a resistor, in place of Z2 we have a capacitor C1. So again equating the current that is flowing through C1 and R1. So we'll get the output expression as E out is equal to minus R1 C1 into derivative of the input voltage, that is d of V in by dt. So its Laplace transformation can also be written in this fashion. So this way we can able to do the circuits using operational amplifier. So starting from a simple unit amplifier or unity amplifier, are also called as a voltage follower, and then an inverting amplifier, non-inverting amplifier with gain 0, gain gain infinity and gain not infinity. We got the expression for the gain in two cases for both inverting amplifier and non-inverting amplifier, with A0 as infinity and A0 as not infinity. And we also say two more applications, that is integrator and differentiator.